to talk about the Briggs-Haldane mechanism of enzyme catalysis. We're going to compare this to the Michaelis-Menten mechanism in a minute. You've probably heard about that one before. But let's go ahead and write the enzyme catalysis mechanism. We have these rate constants written above and below the arrows in the normal notation here. Just to make sure everybody's on the same page. We have product P, enzyme E, and substrate S. I'm going to make a little shortcut here and assume that this last step is very fast. So as soon as I make an enzyme substrate complex and it reacts, I end up going straight through the EP complex onto the enzyme plus the product. So the product release step is very fast here, we're assuming. So this means that this is, for all practical purposes, my mechanism that I'm going to work out the rate law for. I want to find a rate law, an overall rate law for the formation of the product. So if we were to apply the pseudo-steady-state approximation to my enzyme substrate complex, then I would get the rate of formation of that complex by going here. That's this first term. The second term corresponds to loss of the enzyme substrate complex by going backwards. And the third term corresponds to loss of the enzyme substrate complex by going forwards from ES. In keeping with our pseudo-steady-state approximation that we've already learned, we're going to equate that rate to 0. Concentration is now going to be proportional to the enzyme concentration with a proportionality K1S over K minus 1 plus K2. Okay, this is great. We eliminated a catalytic intermediate. We wrote it in terms of another intermediate and a main reactant concentration, which may or may not be changing in time. Take stock of where we are, okay? I still can't really write down my rate law because even though I found the enzyme substrate concentration, I have it in terms of another unknown, this enzyme concentration. So maybe we should apply the pseudo-steady-state approximation again. Well, actually, that would take us nowhere, right? So that would be a redundant equation. We know that it's a redundant equation because we have conservation of the enzyme amounts. Okay, the enzymes are not being destroyed or created or altered. They are just being changed from one form to another. They're going from free enzymes to enzymes bound. And when we set this one to be 0, then we know that we have to also have that the rate of the enzyme is 0. So this is really, in a sense, this would just be a redundant equation. In fact, if you went through and you wrote it down, you would find that it was the same equation as the one before with all the signs reversed on all three of these terms. When you equate it to 0, you don't learn anything new. What can we do instead? Well, throughout all of the catalysis lectures, we're going to have one equation that we can use over and over again, and that's this idea of a site balance, okay? So we count the total number of enzymes that we put into our beaker at time 0, and after the reaction starts running, that's going to be split between enzymes that are free and enzymes that are in this enzyme substrate complex. So these two must always add up to the total amount of enzymes, which is really just to say that the total amount of enzymes here is not changing. Now what we're going to do is go back and write the rate law for the total rate of product generation. So that's going to be K2 multiplied by the enzyme substrate complex concentration. So that's these two terms right here. And now we're going to remember that we have the enzyme substrate complex in terms of the total enzyme concentration. That's a much more convenient variable to use because I know how many enzymes I have. But we can use this equation, insert into this equation. We're going to replace this part with the expression that we got from up here. Okay, so when we do that, we get that the total amount of enzymes is related to the ES concentration by this factor of 1 plus, sorry, let me go ahead and write this in a way that I like it, like this. And now you see that where I had the enzyme substrate concentration in here, I can now solve for this thing and write everything in terms of E total divided by this quantity in brackets here. Okay? So we go through and we do the math on that, and you get an expression that looks like this. Okay, so this is my final answer in a sense. It is customary to try and write this in terms of a smaller number of kinetic parameters. In other contexts of catalysis, we usually write them in so-called 1+ form. We won't do that here. We're going to write this in the form that's familiar from the enzyme kinetics literature, and that's this Michaelis-Menten form. So what we're going to do is divide everything by K1. Okay, so if we divide everything by K1, then we get a bare substrate concentration in the denominator plus this Michaelis constant, K sub m, is K minus 1 plus K2 divided by my K1. And in the numerator, we just killed off this K1 term. This is my final answer. And this is called the Briggs-Haldane expression for the rate law in enzyme kinetics. I want you guys to remember this expression. We had a rate law that it's going to be first order at very low substrate concentrations. As the substrate concentration gets much, much larger than K sub m, it's going to change to being 0th order. Let's do a little sketch of that, just so that everybody sees what we have here. So here's my rate law. This is versus the substrate composition. At very small substrates concentrations, so when we're way down here in this corner, we don't really see this term in the basement, and it just looks like it's proportional to the substrate concentration that lives upstairs. So it's going to start out looking like this. But as the substrate concentration gets large, comparable to K sub m, then it's going to start to turn over and just look like it's approximately a reaction order of 0. This is the point K sub m along this axis where these two things switch. So here we have a reaction order of 1, and over here we have a reaction order of 0. All right, let's go ahead now and talk about the Michaelis-Menten rate law. And the difference between the Michaelis-Menten rate law and the Briggs-Haldane rate law is that we're going to, instead of pseudo-steady-state, we're going to invoke a quasi-equilibrium assumption, okay? And we're going to apply that to a step, okay? We apply quasi-equilibrium approximations to steps. We apply pseudo-steady-state approximations to species. So specifically when we talk about the quasi-equilibrium, what we're going to do is we're going to assume that the association of the enzyme and the substrate and dissociation are very fast. So this process is going to come to equilibrium, almost equilibrium, that's so much faster going back and forth that it barely knows that there's this leak going from here out to the product plus enzyme state. Okay, so this leak is slow, and this back and forth is very fast, and that's what justifies the assumption that these two are going to reach a quasi-equilibrium. They have time to go back and forth many times before this ever happens. So let's see this Michaelis-Menten derivation. We have our enzyme plus substrate goes to enzyme substrate again. We have enzyme plus product. The key thing that we're going to do to make this go from the Briggs-Haldane case, this is really the same as the Briggs-Haldane assumption. And what we're going to do is apply the quasi-equilibrium approximation right here. And now I always draw my quasi-equilibrium arrows as this little double harpoon kind of thing. Okay, so E plus S goes to ES and then E plus P. Okay, so we don't need to know the rates of these two steps anymore. Okay, all we need to know is the equilibrium constant at that particular step. Okay, so if these things are quasi-equilibrated, the forward rate, K1 times ES, has to be equal to the backward rate, K minus 1 ES. You can see that all that matters here is the ratio of K1 and K minus 1. That's what we're going to see down here. Okay, so this Km is going to be that ratio of the K1 and the K minus 1. Okay, so if we let these things be quasi-equilibrated, now I can go straight to my total enzyme concentration, which is again a sum. The site balance, we can always use this. Okay, never forget to use your site balance. First step in a catalysis problem is to write down your site balances and then make assumptions about the relative rates of different steps and maybe fall back on pseudo-steady-state approximations for the others. Okay, so enzyme substrate plus enzyme concentration. I write down the enzyme concentration in terms of the ratio K minus 1 over K1S. This comes from this equation right here. Okay, so we're going to make that, we're going to plug this in. So let me see, is equal to K minus 1 ES divided by K1 times S. And indeed, we can factor out the ES out front, and we're left with K minus 1 over K1S. Okay, so that checks out. And then now we know that we can go through and solve for the ES, and that gives us ES is equal to E total times 1 over this thing in brackets here. So then solving for this, we get that the rate of product formation is K2 times ES, and I have now an expression for ES that I'm going to plug into here. After I simplify, I again get something that looks like K2 times S times E total divided by S plus K sub m. Now this looks like exactly the same kind of rate law that we saw in the Briggs-Haldane case, but the interpretation of the K sub m is different. Okay, recall that in the Briggs-Haldane case, we got K sub m was K minus 1 plus K2 over K1. In the Michaelis-Menten case, we get K minus 1 over K1, an equilibrium constant interpretation for this. So how do you know which is correct? Well, you don't usually. You start out with some data. The data on substrate versus time, for example, might be used to fit a rate law like this. This comes out as a fit parameter, and you really don't know whether the parameter that you got from that fit corresponds to an equilibrium constant, as in the Michaelis-Menten rate law, or to a ratio of rate laws and sums of rate laws, as in the Briggs-Haldane. We will encounter this a lot, that a lot of different mechanisms, and sometimes much more drastically different mechanisms, will end up with rate laws that you cannot actually distinguish from a typical experiment. Sometimes we can make progress towards distinguishing those things with labeling studies. There are also ab initio calculations, that is using quantum chemistry, to get some idea of whether one can be completely ruled out. So then the last thing that I wanted to show here is a Lineweaver-Burke plot. Okay, so let's look at a real situation where the kinetics really obey something like this. So if you look at the reaction that converts ATP into ADP in your body, remember this is this energy currency of the cell, there's an enzyme, myosin, that takes that to adenosine diphosphate and releases a phosphate. We're going to propose that this has Michaelis-Menten or Briggs-Haldane type kinetics. So this is our proposed rate law, and it's really motivated by these simple mechanistic proposals that we already saw. How would we test this? Well, one of the simplest things that we can do, so here's the raw data, the concentration of my substrate, the measured rate. Of course, remember, a lot goes into actually measuring that. You have to think very carefully about ways to get a measurement. And so what we're going to do is just assume here that somebody has done that thinking for us. And then we're going to transform our data. Okay, so we're going to transform it so that we can do a slope-intercept analysis. And the natural thing here would be to take 1 over the rate law and 1 over all of this stuff. And now you see that these two terms in the basement, they will then separate, and you get a term that suggests that we should plot 1 over R, that's over here, versus 1 over the concentration. All right, so this is the transformed version of that rate law above. We write this as 1 over R, and this effectively linearizes this thing. Now we can plot 1 over R versus 1 over the ATP concentration, and this experiment wasn't planned very well. You can see that they did not anticipate the linearization effects here, and so the data becomes very distorted. This is something that you probably want to plan ahead if you can, to think about the fact that when you linearize these kinds of rate equations, you end up distorting your data both in terms of where it falls along the x-axis and also in terms of the degree to which little errors in the measurement get magnified. Complicated stuff that has to do with heteroskedasticity in regression analysis, but that's for another class that I will teach next semester. All right, so the slope we can interpret now, going back to our formula. We know that we can interpret this slope as K sub m over K2 E total, and we can interpret the intercept as 1 over K2 E total. Okay, so notice that the intercept is non-zero here. We're going to something that's about 5. So this plot, the 1 over R versus 1 over substrate concentration plot, is known in the literature as a Lineweaver-Burke plot. Again, widely used, but also somewhat controversial because it does do some of this exaggeration of errors in your data. But for our purposes, it's conceptually appealing to be able to pull these things out of a simple chart that you could create in Excel. You can get confidence intervals on the parameters that you pull out of these things, and of course that's a really powerful thing to be able to do. I think that's it. We're gonna pick up next time with acid-base catalysis, and then we'll go on to heterogeneous catalysis.